So, hello everyone, and today I'm going to talk about probability. So, once again, applied statistics for probability and probability for engineers. This is actually chapter 2, the probability chapter. So, this will be in two parts. The first part will be the lecture. And the second part, I'm going to show you how you can use Excel to deal with the contingency tables on here. So, moving on, general chapter outline, and we're going to go over. So, if you want to quickly look at this, probably will not have time to timestamp all this stuff, but as you can see, this is what we're going to go over: sample spaces, counting, axioms, union and events, conditional probability, intersections, independence, Bayes theorem, and random variables. Our general learning objectives, if you want to see it, pause now, but I'm going to try and keep this as brief as possible. So if you don't want it, if you want to see in depth, just pause right now. So first thing I'm going to talk about is a random experiment. A random experiment is this experiment that is carried out under controlled conditions, and we have no idea what the result is. So the idea is I want to test something. I have no idea what it is, and I'm going to apply some basic rules to it and see what I get. And the important thing is every time I could run this set experiment, I have the probability of getting different results. So basic example is if I'm going to count how long it takes to boil water. Well, I will expect to get different amounts of time each time I boil water based on just pure random chance. Second law of thermodynamics, all that nonsense. So I'm not sure exactly what I'm going to get each time I do it. This leads to something called a sample space. A sample space is just the idea of all the possible outcomes that I can get in an experiment, and that's denoted with an S. Now, the sample space can be either one of two things. It can be discrete, which is a finite or countable number of outcomes. So for example, if I am flipping a coin, my sample space will either be a heads or tails because that's all I can get. Or I can have it as continuous. So in my previous example, when I'm talking about time it takes to boil water, well, depending on circumstances, if the heat's not applied, that time could take much longer. So it could be finite or infinite, and it can consist of all real numbers. So that's the difference between a discrete and continuous. So for instance, let's take a camera flash. We randomly select a camera and record the recycle flash time. S is equal to R plus, which is values greater than 0. We can't have negative time, right? Positive real numbers. So our sample space instantly contains only real numbers, only real positive numbers. And if we know that recycle times are between 1.5 and 5 seconds, then that restricts our sample space between 1.5 and 5. And we know it's continuous between those 2 points. And we tend to have 3 values. So if we could put the cycle time to a low value, medium, or high, and then categorize like 1.5 to 2.5 is low, 2.5 to 3.5 is medium, 3.5 and above is 5, we have created 3 categories and made it discrete. And we can also turn it into a binary. If we have a specific metric that says all cameras must perform cycle times under 3 seconds, then it turns into, does it meet specs? Yes or no? So different ways we could categorize the same information. So this leads to probably one of the coolest things out there, which is tree diagrams. So this is for message delays that are either considered on time or late. And all a tree diagram is a way to categorize what you're doing based on specific metrics. So this is if I'm doing on time or late. So message 1, on time or late, and we could see, as we do message 2, message 3, message 4, the different outcomes, and this would be the total number of probabilities. Another use for these, if you get up to machine learning and stuff like that, is you can make decision trees out of these trees where you have probability of this happening, probability of this event happening here, all leading to a specific outcome down here that you're interested in. And that's another way we can look at it, is assigning probabilities. But this one specifically is just looking at your sample space based on the 4 outcomes of the different messages. So an event is a subset of sample space of a random experiment. So basically, a union, a sub event is just whatever happens. So a union of 2 events consists of all outcomes. So unions are denoted with a U. So this part right here. So unions are when you have all possible outcomes of 2 events happening. So if I am, I'll get to an example later. An intersection, which is denoted with that almost like an N, is all outcomes that are contained within both. So union is all possible between 2 events, and an intersection is all ones that happen in both events. And the complement of an event in the sample space is basically everything that doesn't happen in that event. So for instance, if I am looking at all, let's take sports. If I'm looking at all basketball games where teams score over 100 points as my events, the games that do not have scores over 100 would be my complement. And then that is denoted by an E prime. So E with little asterisks. So that's just everything that doesn't happen in your events. So this is how we actually look at this. So we have, this is the, we're talking cameras, recorded recycle times, and we do it whether or not they're based on specs. So we could do yes and no as Y and N. So all of our possible sample space for 2 cameras are yes, yes. So both of them make it. Yes, no, one makes one, first one makes, second one doesn't. No, yes, first one doesn't, second one does, and no, no, both of them don't. So from that, if we have a subset of outcomes where one camera is denoted as the first event, we're looking at basically all the events where at least one camera succeeds. That gives us everything but this no, no. So our event for that is yes, 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 no, no, yes, whichever one only has one Y. And then E2 is the a subset where cameras do not conform. We can turn that into E2, and that's just no, no. Other examples of events, E3, since we've talked about every event, all the other events, which is E naught, essentially, is null. We don't have any other events that we haven't talked about. And we can have E4 is just the sample space, which is all these outcomes right here. So if we have another one, which is E5, which is Y no, no, Y, and N, and we want to look at the union, all this is set up just essentially to come to this. So if we look at E1, which is yes, 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 no, no, yes, and E5, which is yes, no, no, yes, no, no, remember the union is all outcomes that are contained within the first event and the second event. And so we have yes, 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 no, no, yes. So if you look at the sample space, it's these first 3 here. And then E5 contains no, no, which is up here. So we have E1 union E5 equal to the sample space itself. E1 intersection E5 would be the events that occur both in E1 right here and in E5. So what I end up doing is I look at each one. So yes, yes, does that appear down here? No, it doesn't. Yes, no, yes, no. So yes, no appears. So it's over here. No, yes appears here and here. No, yes, and we have no, no does not appear in E1. So E1 junction E5 would be Y no and no Y. And if I'm looking at this one, the complement of E1, the ones that are not in E1, is just no, no. So back again, we have recycle times in sample space between 10 and 12 seconds for event 1 and 11 and 15 seconds for time 2. So looking at this, the junction would be between 10 and 15 seconds because we have answers, or sorry, the union, not the junction, 10 to 12, 11 to 15. Since those overlap, we go from 10, the low end, to 15, the high end. And the junction, where they have the same, would be between this 11 here and this 12 here. On these, make sure you have the right signs because you need to make sure the signs stay the same. So the 10s here have the is greater than or equal to, and the 15 is less, or x is less than 15, and on here the same as well. So the 11 is less, 12 less. So the complement of E1 would be x is less than 10, or x is greater than or equal to 12. So basically everything but 10 to 12. And the complement of E1 union E2, so we have this part right here, is between 12 and 15 seconds because E2 is 11 to 15, right? And we have this as less than 10, so this does not fit in this. But, say this is the junction, but this fits in this. So this sits the minimum boundary, and that sets the upper boundary. So all these are done in order to bring it to a Venn diagram. Venn diagrams are incredibly useful tools because they help take all these numbers, which can be somewhat confusing, and turn it into something that's visual. This would be a very incredible one to use on your homework because it tells you what you're doing. So this is A junction B, so the parts between A and B. This one right here with the 3 parts here, this will pop up a lot, is A union B junction C. So what is both, so A and B right here, but only in C. So what it's doing is it's restricting it to this part right here. And this part right here, when you just want to exclude 2 regions, is A junction C not. So what parts are junction with an A and C except everything else? And this comes in handy for different things. So a mutually exclusive event is an event where 2 events have no overlap. Those are called mutually exclusive. An example of a mutually exclusive event is if one person draws an ace of spades and another person rolls a 6-sided dice, they have nothing to do with each other because they have no reasons unless you have some weird rules. As long as the 2 events have nothing to do with each other and there's no overlap in probability, they're mutually exclusive, and they're done using that kind of Venn diagram. There's no overlap. If you do have a complement, so the complement of E would be equal to your original event space. These are some wonderful math laws that make sense whenever you deal with your the spreadsheet stuff, which I'll have uploaded soon. So if I have the A union B junction C, that would be the same as A junction C union B junction C. And A junction B union C is equal to A union C junction B union C. The De Morgan's law is the A union B complement is equal to the A complement junction B complement, and A junction B complement is equal to A complement union B complement. And our A junction B is equal to B junction A, and A union B is equal to B union A. So that's just the inflection or fact that it doesn't matter which order we do it in. So all that leads us to some basic counting techniques and how we use those within statistics. We can determine the outcomes of sample space or events if we use some basic math. Counts are the number of outcomes in the sample space, and various events are used to analyze random experiments. And we call these counting techniques. We use multiplication rule, pretty easy, permutations and combinations, which are slightly more difficult, but all are based off of simple math. So the multiplication rules is how we can take a series of sequences of k steps and figure out the total number of outcomes from that. So if we have first step, you have n number of outcomes for n of 1 of step 1, n of 2 for step 2, and n of 3 for step 3. We can find the total number of ways to finish what we're doing by taking those n1 times n2 times n3 all the way up to n to the k to our total number of steps, and that's the number of ways. So for instance, if you're going to be designing a website of 4 colors, 3 fonts, and 3 positions for an image, you take that 4 times 3, and you get 36 different designs possible. This is a good way to quickly tell you how many different outcomes. So if you remember back when we had this tree, we had 2 outcomes, on time or late, and 4 messages. So you take that 4 times 2 is 8. If you look down here, 1, 2, 3, 4, 5, 6, 7, 8. So 2 times 2 is 4. So yes, 6, 8. So a permeation of elements is an ordered sequence of the elements. So we have a sample space of A, B, and it's supposed to be C. ABC, ACB, BAC, BCA, CAB, CBA are all the possible, it's called permeations of the elements. What order can you get things in order for it to be expression of all possible outcomes? So the number of permeations is equal to the basically n exclamation mark, which is n times n minus 1 times n minus 2 until you get down to 1. You do have this operation on a calculator. If you're using TI-84s, I do believe it's in the math. It is also available at different things for random scientific calculators will have it as well. So this is done given this mathematical formula here. So permeations R of n. Here's the actual formula, but it ends up being n permeations over n minus R permeation. So on this one, the examples, we have a printed circuit board, has 8 different locations. So that goes in as n, that's our number, and 4 different components, which would be the R. You turn that into 8 permeations over 8 minus 4, which is 4 permeations. When you actually solve this mathematically, what we're going to do is we're going to take and convert this into, it's technically converted to 1 times 2 times 3 times 4. I mean, that's what we have here. It's 1 times 2 times 3 times 4. And this is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. So what ends up happening is this and this both cancel each other out, leaving the 5, 6, 7, 8, which gives us 1,680 different designs. If you have similar objects, the number of permeations of n, which n1 are one type and n2 are the second type, is n prime, or sorry, n permeations times n of 1 permeation and n 2 permeations, all the way to the n of R permeations. That's essentially how we end up using these parts right here. So we have a total hospital operating rooms have to schedule 3 knee surgeries right here, and 2 hip surgeries. So those are the 2 different types of surgeries we're trying to schedule, and they're all in one day. And that together gives us a total number of 5 surgeries. So we're trying to schedule 5 surgeries, 2 hip, 2 knee. And we need to figure out how many different possible sequences of those we have. So that just turns into 5 permeation, 2 permeation, 3 permeation, which gives us the easiest way to do it is to 5 times 4 times 3 permeation over 2 permeation, 3 permeation. So these will cancel out. That cancels out, leaves this as a 2. 5 times 2 is 10. And then they give you the 10 possible sequences. So that was permutations. Combinations is when your order is not important. You just have to draw them. Number of combinations, subsets of R elements can be selected from a set that's given as N permutation, R permutation, N minus R permutation. So this will be a smaller number than permutations. How we do this? So if we have, this is where you have a lot of work done. I know whenever you do, like a lot of results are a popular one for this, but when you're dealing with defective versus non-defective parts, this is also where this kind of comes up. So if you have 50 parts with 3 defective and 47 non-defective parts, if you pull 6 parts from 50 without replacement, so this is something you have to make sure you do it without replacement, how many samples of size 6 contain 2 defective parts? So where this gets confusing is you can only pull a total of 3 defective parts because we're talking about defective parts, right? So that number goes up top, which is the first part. Let me get rid of that. That was not very good. Then, looking back at the formula, R is our next part, is how many, got 2 defective parts right here, is our R. So then we do N minus R. So 3 minus 2 is 1. So this turns into 2 permutation 1, 2 permutation 3 over 2 permutation 1. Those cancel out, and that leaves us with the 3. So 3 different ways to pull 2 defective parts. So we have 2 parts that we pulled that were defective. Now we have 47 different parts left that are acceptable because 3 defective parts, we have 47 left that fall into the acceptable. So that goes up top. The number of different ways we could do it from here, since we've pulled 2, we have 4 left. So that gives us 4 permutation, 43 permutation. Writing it out, it goes like this: 43, 43, 1, 11, 4, 6 is 23. That cancels out to 15. Multiply that all together, you get 178,365. From here, the multiplication rule, you take those 2 numbers, combine them, and you have 535,000. Possible ways to pull 2 defective parts out of 6. If you want to find out how many different subsets of size 6 there are, that's 50 permutation, 6 permutation, 4 permutation, which gives you 15,890,700 possible combinations to pull out. So when you're trying to pull 2 out, remember, yes, you have 500, like over 500,000, but that's out of 15 million. So it's not nearly as high percentage-wise as it appears. So probability is nothing more than the likelihood of an event happening. So probability works between an assigned interval between 0 and 1. So our probability will never go above 100% and never goes below 0%. So 0 is will not occur, 1 is it will occur. And this is something that happens, if we get to it, we'll talk about it, with logistic regression. The chances of something occurring versus not occurring and how you build up to it. So this is all based around how much are your different interpretations. And I kind of disagree with a relative frequency here, or at least their example. So subjective probability is how much I believe it's going to happen. We assign, I have issues with this, our belief something's going to happen. So when they say they have about a 30% chance of rain, they're assigning that as a subjective belief. I have issues with that because I actually have seen some of the numbers on how and the methods of how they do rain, and it has nothing to do with being subjective. It has to do with very specific metrics that are met with forecasting, but that aside, this is what they give. A relative frequency is looking at how many times an event will occur given a specific number of repetitions. If I flip a coin, how many times do I expect it to be heads? So if you assign a 20% or 0.2% or 2 to an outcome that a corrupted pulse in a digital signal occurs, then that means about 20% of all your signals will be corrupted. So we are assuming essentially fair outcomes. Whenever we have an n number of possible outcomes that are likely to occur, the probability of each outcome is 1 over n. So if you have one laser diode randomly from a batch of 100, that means I have a 1% chance, or 1 out of 100, of choosing any diode, because each of them is equally likely. If I roll a dice, a 6-sided dice, I have a 1 in 6 chance of rolling a 6, regardless of what happens. I have a fair chance. For discrete sample spaces, the probability of event can be defined by reasoning in the previous example. So the probability of event E, which is called the P of E. So this right here, the probability of chance E, of the event E, and that equals the sum of probabilities of the outcome, which we'll get to. So if we have random experiment, we can result in the outcomes of A, B, C, and D. And here are our probabilities for A, B, C, and D. Let A denote events A and B. So here is these two right here, 0.1 and 0.3. So those are A's. Well, the probability of that would be 0.1 plus 0.3 is 0.4. B is BCD. So these three right here are B. So 0.3, 0.5, and 0.1 would be 0.9. And C is just this last event, 0.1. So the probability of that is 0.1. So the probability of A naught is, or sorry, A complement is essentially everything that's not A. So these two right here, 0.5 and 0.1 is 0.6. And the probability of B complement is this one right here, because that's the only one not within B. And C complement are the first three, because those are the ones not in C. So when you start talking about junctions, probability of A and B is I have A here and I have B here. The only one that occurs in both is 0.3, so that gives us 0.3. B union, or A union B, is this one, this one, this one, and this one, all 4 events, because we have all 4 events in both sets. And then A junction C on these two and this, since they don't contain any of the same numbers, then it's null. We have no values. So the probability of A junction C is 0, because there's no chance of getting something in both sets. So really quick, the probability within your sample space will be 100%. If you take up all the probabilities of all your outcomes and add them together, it will be 1. The probability for all events is between 0 and 1. Because you have that values between 0 and 1 for probability, all events will help. You cannot have more than 100%. You cannot have less than 0. The probability of 2 events, event 1 and event 2, within event 1 junction event 2 will be not null. If event 1 junction event 2. So basically, if they don't have overlap, then the union of E1 in E2, event 1 and event 2, is equal to the probability of those 2 events individually. So if you have a 0 probability, then your chances are going to be 0. Probability of a null event will be 0. And the probability of the complement of an event will be 1 minus the probability of the event. And if the first event is contained in the second event, then the probability of your first event will be smaller than the second event, which makes sense. If your first event, you have to have the second event essentially happen for the first event, then the second event's probability is going to be bigger for the first event to even occur. So let's actually get around to explaining what all this stuff is. So the union is that again, junction is that, and complement. So we've been over this, right? The probability of joint events can often be determined from the probability of the events it comprises. So I will make a second video with just this stuff so that it's easier for people to see. So if you have a probability, so if we have H denoting the high levels of contamination, the probability of an individual with high would be the row total over the grand total. And if you C is the center of the tool, the probability of C will be the column total over the grand total. So if you're just looking for one part, it's always row or column over the grand total. So in this, we're looking for the probability of H junction C. So H junction C. So remember, junction is where it's contained in both. So it's actually this part right here, because that contains both the center of the tool and high contamination. So that is 112. And whenever you deal with just simple junctions, it's always each individual cell over the total. So the event H union C is the event that a wafer from the center of the sputtering tool contains high levels of contamination or both. So H union C would be the probability of high, this part right here, the probability of contamination, or sorry, center, high, so these numbers right here, minus the probability of that 112. So I could take 358 plus 626 minus 112 and divide it by 940. Because what you're doing is you're looking at this minus this, or plus this, but since you've actually counted 112 twice, you need to remove that from the event because it's unfair to have more emphasis on that 112. Because it's 872 over 940, which is a very high amount. So the probability of a union is equal to the probability of A plus probability of B minus probability of A junction B. If they're mutually exclusive, probability A union B, or probability of A plus probability of B. If you don't have them overlap, you don't have to worry about it. If you have 3 or more events, A union B union C, probability of each individual event minus probability of junction of A and B minus the probability of junction A and C minus the probability of B junction C plus, because you can't really do these because these are two-way tables, the probability of A junction B junction C. In mutually exclusive events, if you have a bunch of events that are exclusive for all its pairs and the junction is a null set, then the probability of your huge things are the sum of the probability. So a probability of event B under the knowledge of the outcome of A. So this is conditional probability. So if I am playing cards and I want to know what the probability of my card being a spade given I drew an ace. So this is given as B given A. So probability B bar A. So I drew an ace. What's my probability of a spade? Which is 1 in 4. Because if I drew an ace, there's only 4 suits. So I have a 25% chance of that card being a spade. So in this one, digital communication channels has an error rate of 1 in 1,000 bits. Errors are rare, but they occur in bursts. If a single bit is transmitted, we might model the probability as 1 in 1,000. However, if the previous bit was an error because of the burst, we might believe the probability will be greater. So we might say it's a 10% chance. So the probability of an error given a previous error might be 10% instead of 0.1%. So that gives us this formula right here. Conditional probability is calculated as probability of B given A is a probability of A junction B over the probability of A. So probability of A is the chances of A occurring. A junction B is a probability of outcomes A junction B over N. And so the probability of B junction A is given right up here. So in here, so we have parts classified, surface flawed. So we have, does it have a surface flaw? Yes, no, F, complement of F. Is it defective? Yes, no, is D complement. So we want to know the probability that we have a surface a defect given a surface flaw. So what we do with this, a lot easier than it seems, is we just take the table and only care about this part, because we care about whether this event right here occurs given the fact that you have a surface flaw. Since we do have a surface flaw, our total is the column total, and our top number is the numbers that have surface flaws. So the probability of a defect given a surface flaw is 10 out of 40, or 0.25. So if we look at it the other way, the probability of a defect given it is not a surface flaw is this right here, based on the other side. So 18 out of 360, or 0.505%. So sorry, not 0.05, not 0.05%. So 5% versus 25%. So we could see that if you are doing stuff based off of this type of data, I would put more emphasis on making sure that you don't have surface flaws than not surface flaws, because even though the no surface has higher defects, you produce a lot more chips, like 9 times as many chips for roughly half, or not even half, twice as much errors. So, and this gives us the idea of random samples. And here's one of my things that kind of bugs me. So random samples are when you actually can do things randomly. A lot of the times you'll find a lot of studies are done and they don't truly have random samples done. You have to be very careful, specifically when you're looking at like survey data, to make sure that you're not putting something called bias into your samples. For instance, if you are doing surveys in Arizona, specifically Phoenix, you are selecting for people who live in that specific region. You're not going outside of that region for your sample. And even like your school itself will attract specific people, so you have to be very careful on how you draw it. That being said, the easiest way to remove yourself from it and to reduce bias is to do true random sampling. Usually we use a random number generators so that we can remove humans from the equation. I usually use, I don't remember the algorithm itself, but there's like white noise algorithms that set very specific parts to do your random numbers to select for you. And that's the easiest way so that you can't influence your outcome. So the conditional probability definition can be rewritten to provide a formula known as the multiplication rule for probabilities. So the probability of A junction B is equal to probability of B given A minus, which is equal to probability of A given B times the probability of, sorry, I forgot. It's probability of B given A times the probability of A, which is equal to probability of A given B times the probability of B. We can do this essentially by changing A and B, since you can change A and B, right? So an example of this is if we have first stage of numerical controlled machines operations meet specifications 90% of the time, pretty decent. And the probability that it meets specification in the second stage, given you meet specifications the first stage, is 95%. So what are the probability that both stages meet specifications? So using this rule, the probability of B given A times the probability of A. So probability of B given A is that second stage, because we've already met the first one at 95%, and the probability of your first event, which is at 90%, gives us a total specifications of 0.855. So we have like an 86% chance of meeting specifications for stage 1 and 2 respectively. So the total probability rule is, given the fact that A and A complement are mutually exclusive, the junction of A and B, this part right here, and A complement and B, this part right here, are also going to be mutually exclusive, then the event space B here will be the union of A junction B and A complement junction B. So you can take these two parts and add them together. So this gives us the idea of a total probability rule. So the probability of this B space is the probability of B junction A plus the probability of B junction A complement, which is also the probability of B given A times the probability of A plus probability of B given A complement times probability of A complement. So another example, because they love semiconductors. So we have chip manufacturing process and contamination. So if we have a 10% probability of failure given high contaminations, and the probability of being at that level is 20%. And if we have not high contamination, so anything outside of high, the probability of failure is 0.5%, and the probability of being at that state is 80%. So F is the product, is this right here, is failure, and H is your probability of contamination. Then the probability of F given H is 10% right here. And the probability of F given H naught, not high, is 0.005. So the probability of H, high contamination, is 0.2, and H complement is 0.8. So the probability of F itself is 0.1, right here, the probability of failure, times 0.2. So 0.1 times 0.2, and then you have to add in also probability of your not high times your probability of high, and that gives you a total probability of 0.024. Because you had to add the probability of everything together, and the easiest way to do that is to take probability of something happened times the of being at an area times the actual probability, and sum them together. So no matter how many regions, all this says is no matter how many regions you do, you have to apply that rule to how many regions that are in your event space. So yes, it looks kind of annoying, but all this is the same thing that you've done here and the same thing you've done here. So if you have two events and they're independent of each other, if this happens, if the probability of A given B is equal to the probability of A, the probability of B given A is equal to the probability of B, or the probability of A junction B is equal to the probability of A times the probability of B. So I will, in the other video, show you how to actually calculate this in Excel, so you basically get the answer. So the knowledge of that outcome of the experiment in event A does not affect the probability of the outcome in B. And this is how you can mathematically show that. So the events of all these events are independent only if and only if the events for any subsets of the events. So if you have the junction of all the events is equal to the events times each other. So which is kind of what we said here, right? So all this leads up to Bayes' theorem. So this happened in the 1700s, and he was finding probabilities that a condition was present, unless our case was high contamination, given an outcome, semiconductor failure. So the state theory itself states that probability of A given B is equal to the probability of B given A times probability of A divided by probability of B. so long as, once again, the event B has a higher than 0% chance, because you can't have a 0 in the denominator. So in here, we're back to our semiconductors. Probability of F given H. So F failure given high contamination is 0.1 times the probability of high here, 0.2, which we've already done, is equal to the probability of F, which we had previously calculated at 0.024. So 0.1 times 0.2 divided by 0.024 is equal to 83%. So the probability of high contamination giving high contamination given a failure is 83%. So yes, that we had already calculated. So if you have mutually exclusive events, the probability of B given event 1 times the probability of event 1 is equal to the probability of B given event 1 times event 1 plus ad nauseum until e to the event k. Always note on this that you will always have event 1 in the numerator and denominator, so make sure you have both of them. And also your probability of event B is non-zero. So a variable that associates a number with the outcome of a random experiment is referred to as a random variable. So a random variable is basically when you can actually get a number from an experiment itself. A random variable is denoted as an uppercase letter X. An experiment is conducted. The measure value of the random variable is denoted as a lowercase. So a random number will be different from a real number based on the capital itself. So random variables are capital. The real number is not, is a lowercase. So a discrete random variable is a random variable with a finite range, so between two specific outcomes. Continuous random variable, and where you can only get a whole number, you can't get a partial number. A continuous random variable is a random variable with an interval of real numbers for its range, where you're going to have any random number to whatever degree. So continuous is electrical current, length, pressure, temperature, time, voltage, and weight. Discrete is number of scratches on the surface, proportion of defects among 1,000 tested, number of transmitted bits received in error. We have specific numbers that are kind of hardwired in. That's how many we get. Versus I can, get finite amounts of pressure or temperature depending on how accurate my measurements are. So there's all the important terms and concepts, and that's essentially what we have for this lecture. So if you want some information on how to do those two-way tables to look at junctions and unions and Bayes theorems and all that, tests for independence, look for my next video. It will be appearing soon. Until then,